Cool. Well, let's get started then. Let's jump in. Let me go ahead and start sharing my screen here. Cool. Okay. Can you guys see my screen?
Yes.
All right.
Yes.
Okay. So recap real quick. Kind of what we left off with last time was we were looking at a new formula that was generated because there's this new idea of being able to compound something continuously. So you got to think of when it's continuously, it means that it's like every single moment of every single day there is some compounding happening, and so it has some benefits in terms of investing, right? And so we're going to be able to look at that a little bit more closely with the next few examples. But the formula specifically is nice because there's less to worry about. It's only determined by the initial amount, which is A, the rate, and the time, right? E is not a variable because E represents a number. And if you guys remember, E is actually rounded off to 2.718, right? So roughly approximately equal to that. All right, so we left off last time kind of looking at the APY and the growth rate. And so now let's see what kind of effect it'll have on our money. Okay, so for part C of the problem, it's asking what is the balance in the account after 2 years and what is the balance after 42 months. So for us, remember that time is always represented in years unless we're told otherwise. Okay, so if we wanted to solve for C or for part C, then we start with a final value formula equal to the initial times E to the R times T power. Okay, we know that the initial investment that she made was $500, and we know that the rate of interest is given by 0.02%. I'm sorry, 0.02. So okay, and then the variable that we're given here, the information is after 2 years. So then we can utilize 2 for time. Okay. All right. So let me use Desmo's calculator here. Slow today. Cool. Okay. Oh, somebody joined. Let's see. All right. So we had 500 times E to the 0.02 times 2, right? So that tells us there that in about 2 years, compounding continuously at a 2% rate, we end up with about $520. Okay, so final value here will be 520 with, I believe it was 41. Yeah, we could round it to about 41. Okay, 41 cents. Right, so it's a nice, easy formula for us to use. We get a nice result. Okay, so that was part C. And then it also asks how long after 42 months, right? So the key part here is to understand that when we're dealing with time, and time is represented in years, you have to make the conversion from months to years before you plug it in, right? You obviously don't want to plug in 42 because then that would mean 42 years, right? So you don't want that. So first, for part D, go ahead and make that conversion, right? 42 months, but there's only 12 months in a year. So you can then go ahead and say that 12 goes into 42 3 times. And then you have 6 months left over out of 12. So 6 out of 12 is just half. So we can just say like that's 3.5. Okay, so 3.5 years, same idea. Now we go ahead, plug it into the formula. So our final value here is going to be 500 times e to the 0.02 times 3.5. Okay, and so let's find out how that changes. Oh, I did something wrong. Power, there you go. Okay, so after 3.5 years, then you're looking at a final value of 536 with 25 cents. 536 with 25 cents. Okay, so not that much more. The reason why it's not growing as fast as you would think, right? Even though it's compounding continuously, is because you have such a small interest rate at 2%, and your initial value is only $500. So it doesn't work for you. I mean, it doesn't grow for you as fast than if you had a slightly larger interest rate or a larger initial amount to begin with. Okay. However, when you make comparisons to something else, if you were to make comparisons to, oh wait, sorry, this is not part D. This was just part C, but the second part. My fault. When you make comparisons to compounding continuously versus compounding, let's say quarterly, you'll see a difference there. It's just not a large amount. All right. Okay, so pretty easy, just plug in. Okay, and then now for part D, the question is how long would it take for the value of the investment to double? Okay, how long would it take, right? So we're not given time. We have to find time. Okay, so that's what we're gonna look for. How long is it gonna take to double the investment? Well, if the original investment was 500, then we're looking to see the final value should reach 1,000, right? Because that's double of 500. So for part D, okay, we're solving for time. We don't know, okay? But the final value will be double the investment. Okay, so if the initial investment was 500, like I said, then F is going to equal 1,000, right? So if we're rewriting our formula, F equals A times E to the RT, then we know that what we're trying to get to is 1,000. The initial was 500. E, it's a constant. R, we know the rate, it's at 0.02, but we don't know time. So whenever you are solving for the variable and the variable happens to be as part of the exponent, we got to use log. But in this case, because we have e, I'm going to teach you something real quick, something that you usually learn in pre-calc or like at the end of algebra 2, is that e, the number e, has an inverse, which is something called the ln, which is known as the natural log. Okay, now I don't know why they put ln when it's natural log, right? It seems like it should be nl, not ln. But the idea here is that these two, e and ln, are inverses of each other. So although before we've utilized log with let's say with different bases, whenever you're dealing with the letter e, you have to use the natural log. Okay, so it's a very specific log that you have to use. So not just any log will help you get rid of e. You have to use natural log, right? So when we get to solving this problem, there'll be a point where we have to use it because we have to get rid of e, all right? Okay, so let's go ahead and try that. If I wanted to solve here, and I want to solve for t, first thing I would do is probably divide both sides by 500. Okay, so 500's gone, and 1,000 divided by 500 is just 2. Okay, now you're left with 2 is equal to e times 0.02 t, right? And so this is where the natural log comes into play, because what you want to do is say, okay, I need to somehow bring this t down, okay? But the entire thing is part of the exponent. So then what's nice about ln is that when you apply the natural log to both sides, ln and ln, and ln and e cancel each other out. Okay, so then what comes down is 0.02 t, and it's equal to natural log of 2. Okay, so then if we wanted to solve for t, all that's left to do is divide both sides by 0.2 or 0.02. And so t is going to equal the natural log of 2 divided by 0.02. So if we really want to know what that equals, let's go back to Desmos and let's plug it in. Okay, so if you do ln, I'm not sure if it'll work if you just type it. Oh yeah, it does. Okay, so you can just type in ln and then parentheses and put a 2 inside, and then that right there, that number represents the natural log of 2. But then we're dividing this by 0.02. Okay, so then the time that it's going to take for the investment to double is going to be 34.65. Okay, so almost 35 years. So we can change this to approximately. Okay, 34.65 years, but basically about 35 years. Okay, are there any questions on the natural log or how we use it? We're okay. All right. So whenever the variable e pops up, or the letter e, know that in order to get rid of it, you use natural log. So you apply ln, very similar to how you applied log. The only difference now is that typically when you use log, let's say for example you had, let's say you had 2 to the x is equal to 5, right? And when you applied log, what you would do is say, okay, when I have log, what that allows me to do is bring the x to the front, but I still have log 2, right? The big difference between ln and e is that they cancel completely, like they're completely gone. Versus when you apply log, log doesn't cancel anything out. Log still stays, and then you have to then divide both sides by this log of 2. Okay, so that's the small difference between the log and the natural log, is that natural log only works with e. Okay, ln only works with e. Log is then utilized for anything other than e. Okay, so anytime that this base right here, anytime this base is not e, then you have to use log. Okay, I hope that makes sense. Send me a little reaction or something, like a thumbs up or a clap, just so I know. No? Okay. All right. Anyway, moving on. All right, so let's take a look at number 5 now. So this is all for number 4. Number 5, we get to do a little bit more work here. All right, so an initial investment in a startup business of $1,500 is to pay an APR of 4% compounded weekly. Okay, so notice how they've gone back, right? That they're not compounding continuously. They're letting us know that they're compounding weekly, right? So the future value of the investment is, and then it's given to us. So what they're using here is the setup of the original formula from compound interest from way back from investigation 3, right? So in that case, the setup for that was, if you remember, was A times 1 plus the rate over the N, and the N represented the compounded how many times it was compounded in a year, and then the power was n times t, right? And so what they've done here is that they've plugged in everything that they're supposed to, right? You have your rate, which is 4%, okay? And they turn that into a decimal, and that's how we have 0.04. The weekly, right? Weekly is weekly amount of times, well, the amount of time, the amount of weeks in a year. And so since there's 52, right, then we see the 52 represented for your n value, okay? The 1500 was the initial investment, and then that shows up as your a value, okay? So everything is there where it should be, all right? So then the question is, what write a rule for B of t, okay? So B of t is our final value in this case, if the interest is instead compounded continuously, okay? All right, so let's just talk about compounded continuously formula. That final value formula, in this case, we're using B of t, so B of t should take the general form of a times e to the r times t, okay? So remember, with compounded continuously, the benefit of that is that you don't need to utilize the n value, right? Continuously means e, all right? So you're gonna use e, which is already there as part of the formula. So then instead, right, your initial value, which is the 1500, that's gonna represent a, so you have 1500, you have e, right? You have to identify the rate, okay? So the rate is 4%. So then in this case, we change that to a decimal. So that's gonna be 0.04. And then the time, that's the thing that we don't know, right? They haven't told us to calculate anything yet. So we can just leave it as a t. And then all of this is equal to b of t. Okay, so the only difference is that it's in function notation, right? Function notation is just, you see b of t because t is the input. If you were to change the input, right, you get the output. But that's the only difference, okay? So there it is, the difference between the compounded weekly formula versus the compounded continuously formula. All right, any questions on that part? Pretty easy, I think. Okay, and then it says, how does the approximate future value producing using continuous compounding compare to the future with weekly compounding? And why does this make sense? Okay, so how does the approximate future value using continuous compare to the future value with weekly compounding? Well, the big thing here is, think about the n value, right? With e, we had something where the limit of the n value was approaching infinity, right? That's where e comes from, is that the n value will continue to get larger and larger and larger. Now think about this weekly problem. The n value stops at about 52, right? So at 52, though it's a somewhat large number, is not as big as reaching infinity, right? 52 is a very comprehensible number. So why are they so similar? Well, it's because they essentially take the same form, right? They take the same form. It's just that with E, what you're doing is you're pushing that n value up about as far as it can go, so that you arrive at that constant number of 2.718. Okay, so you're kind of multiplying by a factor of 2.718, which is something that this is kind of approaching. Okay, so it's a little bit of a tricky question, but it's just trying to get you to see like that the limit, the fact that you're pushing n up is what makes it similar to the weekly, because the weekly pushes up about as far as you can go when you're doing it at certain intervals of the year. I think the largest one you can go up to is maybe like daily, and then that would push the n value up to 360. Okay. All right. So I think B is definitely more of a discussion type problem. Okay. All right. So now let's take a look at part C. Okay. So suppose that the interest was compounded daily. Estimate the investment accrual after 5 years. Check your estimate by calculating this balance using 360 days a year. Okay. So what they want us to do here is to set up something where we're going to get compounded daily, right? And so we were just kind of talking about that. When it's compounded daily, it's not continuous, okay? It's a fixed number, which is 360, okay? Estimate the investment accrual after 5 years. So T in this case will be representing 5. And then check your estimate by calculating this balance using 360 days a year. Okay, so they're telling us what the daily is. It's 360. All right, so it's not continuous. All right, we have to calculate it on a daily basis. So if we wanted to do so, then that would be B of T is equal to 1,500 as the initial investment, 1 plus the rate. The rate is still 0.04, but my end value is 360 now. To the 360, and they're telling us the time, and the time is 5 years. Okay, so let's see what we get. All right, so we have 1,500 times 1 plus 0.04 divided by 360 to the 360 times 5. Okay. All right. So if you can see that, that tells us there that the value of the investment after 5 years is going to be 1,832 with about 8 cents. Okay, 1832. So B of 5, right? So the balance after those 5 years is going to be 1832 with 8 cents. Okay, so you see the questions are kind of jumping back and forth between continuously, daily, right? So you got to understand, like, when I see certain keywords, then I know that I need to utilize different final value formulas. Let me just confirm. Yeah, okay, we're good. All right, any questions so far? How are we doing? All good so far? Good morning. What's up, Angel? Okay. All right, let's move. Let's keep it moving then. Okay, so then here's where the interesting part happens, right? Is where you get to see the comparison between what does it do when I'm compounding quarterly versus monthly versus continuously, right? Well, which one is the most beneficial for my own account, for my own money, right? So first off, for number 6 is we're just writing the formulas. Okay, so write an algebraic formula for the future value of an account. They all have an initial investment of 15,000. T years, right? So that means we don't know how many years, so T is going to remain a variable. We have an APR, so we have the rate, right? Percentage 1.75 under each of the following conditions: compounded quarterly, compounded monthly, and compounded continuously, right? So we got to come up with 3 separate formulas, one for each scenario. All right, so let's go ahead and do that. If I'm doing quarterly, all right, then I have a fixed number of compounding periods in a year, and that would be represented by 4. If I have monthly, then my compounding number is 12. And if I'm compounding continuously, then I don't have an end value, because in this case, I'm going to be using a formula with E, okay? So if we were to write this out, because it's quarterly, then I have to use a final value formula, the old one, right? 1 plus R over N to the N times T. So then this formula will say F is equal to, well, my initial investment was 15,000. 1 plus my rate is 1.75. So when you convert this back, move the decimal 2 spaces, that'll be 0.0175. You make sure you use the entire interest rate there. All right. And then the quarterly represents 4, right? So it's happening 4 times a year. And then you see that 4 show up one more time as part of your power, right? You have n, so it's 4. And then we don't know time, right? Because we're just given information enough to write a formula. Okay, so that's our quarterly interest. I'm sorry, that's our compounded quarterly formula. If we do monthly, very similar. The only thing that's going to change is the n value. So here we would get f equal to 15,000 times 1 plus 0.0175. But this time we're dividing that rate over the course of 12 months. And then you have 12, power of 12 with t. And then for continuously, it's even simpler, right? Because you don't have to worry about the n value. That's not going to be part of your formula. So we have final value here is 15,000 times e to the rate. In this case, it's 0.0175 times t. Okay. So those are the 3 scenarios that we have. So we're going to use those on problem number 7, because then they ask us how much interest is earned in 48 months under each of the 3 conditions, right? How much interest is earned in 48 months under each of the 3 conditions. All right, so first thing is they're trying to trick you here by giving you months. Remember that everything, even when it's monthly, right? Even when it's compounded monthly, t is still represented in years. So 48 months, divide that by 12, and we're talking about 4 years. Okay, so 4 years, that's our t value. Okay, so what we get to do here is do a side-by-side comparison of how much money are you going to get in each account after 4 years, based on whether you chose to do something quarterly, monthly, or continuously. Okay, the more frequently something is compounded, the more money that should result in the account at the end of those 4 years. So you should see that the continuously compounded formula generates the larger return on the investment compared to monthly, and then compared to quarterly as well. All right, so let's just go through, let's actually do the calculation and we can see what we get. So final value will be 15,000 times 1 plus 0.0175 over 4 to the, in this case, 4 times 4, right? 4 years. Okay, so real quick, let's jump over to decimals, see what we get there. So 15,000 times 1 plus 0.0175 divided by 4 to the 4 times 4. And so what we're looking at there is 16,078 with 76 cents. 16,078. Okay, so that's quarterly. So then we should expect that monthly is going to generate something a little bit larger. Because it's such a large amount, we might see the difference even happen in dollars perhaps, but I wouldn't be surprised if it's only just a few cents. Okay, so now next one for monthly, 15,000 times 1 plus point. Oh, wait, I put the wrong, this is 0.075. Messed up. Okay, sorry, it changed the final value by a little bit. 1685 with 16 cents. My fault. I typed it in wrong. Actually, probably round that to 17. Okay. All right. So now 15,000 times 1 plus 0.0175 divided by, this time by 12. Okay, to the 12 times 4, right? And there you see a slight difference, right? Same amount of money, same interest, different compounding times per year. It generates about maybe another dollar, $1.65 or something. Okay, so 1686 with 80 cents. Okay, so slight difference there, right? Slight increase. Okay, and then now let's take a look at what continuously can generate for us. All right, so 15,000 times E to the 0.0175 times the 4 years. And if you can see this value down here, then that's 1687 with 62 cents. Okay, so 16. Okay, so you see it's a slightly larger amount. Okay, from quarterly to monthly, it was about $1.63 more that you earn if you do so monthly versus quarterly. And then if you were to then make the jump from monthly to continuously, there is a gain of not quite $1. It's about 18 cents less, so probably about 82 cents. Okay. So the benefit of continuously, yeah, it's slightly more, but again, it's not like huge. It's not a huge amount. Okay. Any questions so far? Is this too easy for you guys? Like, is it kind of boring? No answer. Okay. Are you guys there?
Yes.
Yes. Dormidos. Wishing you were in Mexico.
Mister, this is how we are in class either way.
I know that's true. I was like, this is no different. This is no different. I should be comfortable with this.
Yeah.
Okay. All right. Okay. So then that's the idea there. Okay. So that's it for number 7. All right. So 6 and 7 were kind of like combined. All right. We're gonna skip number 8. It's not a very good problem. Not very important. Let's take a look at 9, just because it has a little bit of a graphing component. So let me screenshot it first, and let me bring it over. All right. So I've been working on a puzzle like this past couple weeks, and I finished last night this 2,000 piece puzzle. Pokemon. It's cool. I posted on my Instagram, but I think the only one who follows me is David.
Mister, what's your like your actual Instagram?
My actual Instagram is just my name. Like, one word, Noel Somoza.
Because I think you commented on the meme page, and like I saw it, and so I clicked on your account and I thought your pictures were nice. So I just wanted to let you know.
You saw a picture of my what?
Your pictures were nice.
Oh, thanks.
I was like, you can tell you're a photographer.
I know, right? Didn't I teach you photography?
I don't know. I think so.
I think so. I tried to teach you. I don't know if you learned anything.
No, yeah, I do. Like when I take pictures now,
Uh-huh.
like I use rule of thirds now because like I don't know. Ever since like I can't just take a picture because it like it bothers me.
Yeah, that's good. That's good. At least, yeah, that one small thing makes a big difference.
And then like portraits like yeah like well yeah like yeah I don't know.
It's good. It's good. Sorry, my wife is complaining about her. She hates math, but she loves me. So I don't know. I don't know how that works. Okay. What's up, Luis?
Luis.
Luis. Dropping in for a special appearance. I like how he showed up about 45 minutes late. Like we're almost done. But I'm glad you're here. All right. So hopefully you'll catch this last part. All right. So suppose you invest $500 in the local credit union right? And again, it's kind of giving us like this breakdown of a quarterly, a monthly, and a continuously. We have the same APR. And so they want us to write functions using function notation. So we have F of t, G of t, H of t. Describe how the rules are similar and how they are different. Based on your understanding of exponential growth, describe how the graphs are similar and how they are different. And on the same coordinate grid, use algebraic reasoning to sketch graphs of the three functions. Okay, so I think what we're gonna do here is let's first write the functions, and then we kind of understand how they're similar and different, right? That's more for like discussion purposes. We want to look. I want you guys to see how the graphs look in comparison to each other, right? Because we understand algebraically that one is generating a larger value than the others, right? Compounding continuously allows your money to grow slightly more than monthly versus quarterly, right? So how does that look like on a graph? Well, you should expect that on a graph, one of them is going to grow faster than the other two. And so that's just what I want to do, just to compare. And then we'll probably wrap it up. We'll probably wrap it up for the day. Okay. All right. So number 9 here, F of t. We're looking at something that's being compounded quarterly. Whoa, what happened? All right, compounded quarterly. So we have an n value of 4. G of t is compounded monthly. So we have an n value of 12. And then H of t is compounded continuously. So we have E, right? Okay, so the rule or the function for F of t is going to equal, because we're compounding quarterly, this is the old compounded interest formula, right? So we have an initial investment of, I believe, was 500. Okay, 1 plus your rate. Your rate is 2%. Okay, so then that's what we convert to a decimal. So that should be 0.02. So we have 1 plus 0.02 all over the quarterly, right, which is 4, to the 4t. Okay, so that's F of t. G of t will be very similar because now it's just compounded monthly. We change n from 4 to 12. So G of t will equal still initial investment of 500, 1 plus the interest rate divided by 12. And then you have a power there of 12 to the t. Let's see what's going on here. Are you outside? Yeah, I'm in Hawaii. You missed the conversation. No, I'm kidding. This is just a cheap background. But yeah, I am outside. That's probably why you hear like birds, and there's a dog barking out here right now. All right, and then h of t, last one here, is going to equal 500. This time, because we don't have a compounding factor, we're just utilizing e, then to the 0.02 t, okay? So notice how the power is slightly different on the compounded continuously formula, because your power is represented by the rate and the time, not the number of compounding periods, okay? So those are the three formulas. We have F, G, and H. And so what I want to do is just make a comparison, visual comparison between the three. And it says to sketch, but I think you guys can just go ahead and like follow along with me on Desmos and just kind of get an idea of how the functions are behaving.